Good morning. Wow, what an act to follow. That was amazing. We will do our best. So first I want to say thank you to the APSA Foundation as well as the Grants Review Committee for enabling and graciously supporting some of this work that helped me get started. Obviously, the last 2 to 3 years have been incredibly difficult on all of us, in particular on our patients, but it's through opportunities like this that enable us junior surgeon scientists to get started. So I'll talk a little bit about some of this, of the work that was funded. I have no disclosures. So over the last 50 to 70 years, we've made dramatic improvements in the survival of allografts and patient survival and transplants. In particular, with reference to liver and kidney allograft survival, at 5 years, we're now at about 80%, greater than 80%. This is due to several advances in procurement technique, as well as perfusate solutions that have allowed for longer and more stable distance traveled for organs. Also, comfort with microvascular techniques in smaller grafts, especially the ones in our patients in the pediatric population that have overcome obstacles that we encountered during the early 90s. And the advent of more stable and better immunosuppressive regimens, such as the introduction of TAC or tacrolimus in the 90s. So we're pretty good at getting patients over the initial perioperative outcomes and even into the first several years post-transplant. But really what I wanted to focus on was how can we get to longer success? How can we prolong the life of the organ so that it's one organ per one patient? So I wanted to focus mainly on one of the things that I think most people think is related to this, which is the immunosuppression, the necessary immunosuppression that we have to give to our patients, but over the lifetime and the incurred morbidity that's associated with them can lead to things like cardiac disease, chronic kidney disease, and then even in some cases, kidney failure and ultimately kidney transplant. So we've focused a little bit about on a lot of the medical regimens, and some investigators have turned their attention to focusing on cellular therapies. And a lot of investigators have focused on the adaptive immune response and specifically T regulatory T cells because they're thought to be the effector arm of the peripheral tolerance. I wanted to take a step back to take a look at maybe some of the effector cells that may be important for controlling T regulatory T cells, and specifically myeloid-derived suppressor cells, which are an innate immune population, or heterogeneous innate immune population. If we look back into literature, we can see that myeloid-derived suppressor cells, or MDSCs, there's a lot of interactions with T regulatory T cells, and they function to expand these cell populations through different soluble factors and also potentiate their response. So myeloid-derived suppressor cells arise in multiple inflammatory states. They express things like GR1 on their cell surface. They're composed of two populations, mainly granulocytes and monocytes that are identified by either Ly6G or Ly6C. And again, these are just cell surface markers that'll be mentioned later on in the talk, but it also help facilitate us identifying these cell populations by flow cytometry, either in vivo or in vitro. Really, their hallmark, though, is that they suppress adaptive immunity, both in vitro and in vivo, and they express inflammatory and anti-inflammatory cytokines. They provide also immunity to infection through the production of reactive oxygen species, and as I said, a population or a separate population of these cells are granulocytes. So what I wanted to try to understand was whether or not I could exploit or modulate inflammation to help innate immunity have a more immunosuppressive response, which sounds almost counterintuitive. But I did turn to one of the more readily available FDA-approved adjuvants, because adjuvants cause inflammation, to see if I could do that. So I looked at aluminum hydroxide, in particular, that I'll be used to add, what I will call alum. Alum is used in multiple vaccine preparations, and its mechanism of action is thought to be through the inflammasome. So the first thing I had to show was whether or not this adjuvant administration or adjuvant conditioning could expand MDSCs in vivo. And what I did show was that you were indeed able to expand these cells in vivo. But as I said, the hallmark is whether or not they could suppress T cells. And so if I isolate those cells from an adjuvant conditioned mouse and then now co-culture those in a T cell proliferation assay, I can show that you're able to suppress T cell proliferation. But really the question I was trying to get at is whether or not I could utilize this regimen to provide an immunosuppressive milieu in which I could transplant an organ, or in this case, islets. So I utilize this classic transplant model of islet transplant, whereby we take biopsy islets and transplant them into C57 black 6 mice that have been made diabetic. We then insert our adjuvant conditioning regimen, whereby we administer adjuvant sometime between their inception of diabetes and then follow them for survival. And surprisingly, what I was able to find was that in those mice that were adjuvant conditioned, indicated here in red, compared to those that were administered saline, we were able to provide a delay in rejection and increased survival following adjuvant conditioning. While we attributed this to the myeloid-derived suppressor cells, or the MDSC population, we had to prove that. So we had to block MDSCs and show that without them, maybe we would not have the same type of protection. So to do this, we used anti-Ly6G, which again is the granulocyte marker for MDSCs, or anti-GR1, which would essentially identify all of the MDSCs, and used a blocking experiment compared to isotype control. And what you can see is that if you knock out the expansion of Ly6G, the Ly6G population, or all of the population of the MDSCs, you lose that protective effect. Again, suggestive of the fact that MDSCs are responsible for this observation. So next I wanted to try to focus on maybe this axis between MDSCs and Treg, the Treg population, and specifically maybe some of the soluble factors. Well, I know that IL-10 is important for a lot of these immunosuppressive sort of interactions, and so I wanted to try to understand whether or not IL-10 was affected after adjuvant conditioning. So if you look at whether or not MDSCs do express increased amounts of IL-10 following adjuvant conditioning, either in the monocyte populations or the granulocyte populations indicated by MMDSCs and GMDSCs, you can see that adjuvant conditioned cells do express more IL-10. And indeed, if you block IL-10 in the same sort of regimen where you're doing the islet transplant again, followed by adjuvant conditioning, you can see that you lose your effect. Again, suggestive of the fact that IL-10 is likely important in this system. So just to summarize, if we take our transplant recipient and we adjuvant condition them, we can then get an expansion or a myelopoietic response in the bone marrow and the spleen, which then increases and expands MDSCs to provide an immunosuppressive milieu through soluble factors and direct interactions, in which we can place our transplant and perform our transplant, our allograft transplant, which will then increase potentially peripheral Tregs and hopefully happier recipients. With that, I'd like to finish by thanking my lab, in particular Jifu He, who has helped with a lot of this work, and my senior mentor, Jim Markman. And of course, without the support of the APSA Foundation, none of this would be possible. And of course, my department and the Department of Surgery Startup Fund. Thank you so much, and I'm happy to take questions.
Questions from the audience? I am not a transplant researcher, but I read your report, and I saw you had a little bit of concern about the role of a basic scientist and a surgeon. What would you recommend to future colleagues that have the same career plans? What have you learned in your career so far? What the good things are and what things are to avoid?
To becoming a basic scientist, engineer? Yeah. So I think perseverance is important. You have to have a passion for what you're doing. There's been a lot of talk in terms of what the best options are in terms of like how to study or how to pursue a focus. Ideally, if you could choose a focus that's within your realm of your niche, then all of the research, the ideas will flow into each other. If you have to do a separate niche, and seemingly, being a transplant surgeon and a pediatric surgeon, immunosuppression may seem like more of a medical topic. They do flow into each other. So I think it's important to get topics that are very well related so that you can stay on top of all of these things together.
One quick question.
Nice talk. Thanks. Hiroshi from UC Davis. I was curious how you saw the use of this potentially clinically as so to increase the organ lifetime. Do you foresee yourself needing to give an ongoing sort of low-grade inflammatory stimulus? And how would you sort of place that in juxtaposition to using prednisone that suppresses that?
Yeah, no, that's a great question. Some of the other data that I did not have time to show you is that if you look at the survival curves, and this is also borne out in one other manuscript, I think we understand myeloid-derived suppressor cells to be important for the early part of the response, which then coupled with a Treg response, which would be long-lasting. And so my goal, my ultimate goal is to try to figure out how to liaise the two populations and how to make that more antigen specific, because antigen specificity is a hallmark of tolerance. So if I can do that through model antigens, which is the next step in the project, that would be ideal. Thank you for your question.
Thank you very much.
Thanks.